I've been told by so many people on the common that they know they're here, but they've never seen them. And this is why it's important. I cannot explain quite how much joy this brings me. If anyone else comes, they will run. That is just pure luck. Absolute pure luck. So you're not going to get a video now because I'm just going to sit here and watch this. We're about 300 metres from thousands and thousands of people, but we've left a bit of space, and nature uses it. And maybe the whole point of ecology and knowing what's going on is we really need to get over ourselves and let nature exist as well. Okay, excited ecologist, sat on Banstead Common, here just to give you a little rundown of directional selection. So this is now not selective breeding, although it's a natural process. Selective breeding is a natural process that we have hijacked and jumped on the back of and sped up because, of course, we can intelligently pick. Everything I'm about to talk to you about is simply accidental in many ways. Life and death. If you don't have babies, you disappear from the gene pool. So all your alleles didn't work. And that is the element of survival of the fittest. If your genes and your mix of alleles is not good enough to have babies, then you go from the gene pool. So this is now how different selection pressures, of which there are many, lead to adaptation and selection. That could be physiological selection, so the internal workings of an organism that we cannot see. It could be behavioural selection, so the deer that I am still just marvelling at the beauty of is timid and only comes out when it's really quiet. That's a behavioural adaptation. And those alleles will enable her to survive, to have babies, to carry on in the gene pool. Or it could be an anatomical feature. So something about the body, the measure of the alleles that give a particular characteristic, an outward sign of how the organism is constructed, and that might help it survive. So we're actually going to look at not the excitement of the deer, we're going to look at grasses, just to give you an idea of the two types of selection. Yes, directional selection, but then also what happens once you've got the direction right and you're ready to have your alleles honed and perfected, which is stabilising selection. Okay, so in the shadows, because this is a conceptual moment, there is the silhouette of grass. Let's call it the original grass. A monocotyledon has a single seed leaf, so you've done classification. We know that it is a more ancient plant in terms of dicotyledons and monocotyledons. It does flower, however, so it is still a flowering plant. But many, many millions of years ago, there was grass. Now, within grass, there was a huge amount of genetic diversity, different alleles to do different things. And those alleles sit, and whilst the environment remains the same, and this is the absolute key, environmental change and time are required for selection, because selection only occurs at the point of reproduction. So, there is our grass. Let us say, for example, that the environment gets hotter. The environment changes, it gets hotter. Now this grass, many of them grew in boggy, swampy land. And as the climate warmed and the sea levels went back, receded, there was less available water. And so therefore you suddenly would select for any of that genetic diversity where the alleles allow a plant to survive a bit longer. And so that prehistoric plant happens to turn and be selected for this species of grass. However, there were some areas where this original species grew that stayed wet. So on the left hand side we have our dry tolerant grass, but also there were places where it stayed wet, so it didn't select for that. But there were low light levels, and if there were low light levels and it was always in shadow, say, it was surrounded by taller plants, then in actual fact the small ones would die out. So we suddenly have a different selection on our original proto-grass, and we have one that selects for the taller you are, the more light you get, the greater the chance you will survive. So therefore they are selected for, and you end up with a very tall species of grass. You can see it's taller because it doesn't fit. So from one species, our shadow that comes and goes, we have a selection of the environment where it went dry in some places, that's selected for one thing, and then it was shady in another place. It was having to compete with other plants for light, so those that grew taller could survive better. But then what about ones that perhaps grew in very windy places? Both these grasses are very fine and very thin. Their feathery flowers could be blown by the wind successfully, but they could also be damaged. So perhaps then in another place, our original grass is selecting alleles where it's sturdier, so it can withstand the wind. And we have our sturdy grass. Now what you have here is from our original, our shadow, our ancestor that is no longer here. We have our dry adapted grass. We have our tall grass to compete with other species for light. And we have our sturdy grass for the windy exposed areas. And all these can come from one population as long as you have genetic diversity. So not only is directional selection showing the environment acting on the gene pool, success and failure, but it also shows that if you have one species across lots of places, you then can change the environment differently in those places. Yes, you then require isolation, that is true, but that comes later when we do evolution in more detail. But depending on how the environment changes, different alleles are picked. It's like having a complete mix of Lego bricks. And you walk into one room, they say, you have these 10,000 Lego bricks, you need to build a house. Well, from those 10,000 Lego bricks, you can build a house. You walk into the next room and you have your 10,000 Lego bricks. They're exactly the same bricks, but now they say build a rocket. You build a rocket. The amount of different things and slight changes you can do to all those things lead to this directional selection. Right, so let's go to a graph. If you have got frequency up here, so that's F, frequency, so how often an allele happens for a particular trait. So let's just talk about height in the grasses. And then across here, across the x-axis, you have your variation, your different alleles, okay? So we're going to draw a bar graph because it's non-continuous data, if you like. And essentially, in any population, what you would expect to find is that you have a wide range of different alleles. You have some very short, some incredibly tall, and then you move into the middle. And the middle often wins. When we use the word normal, it is a mathematical construct, and it is the idea of a normal distribution curve. Okay, so this is small, this is tall, and you only have a few in each point there, okay? And then you get to the middle, and it could be anything. You can insert whatever you like there. And what you find is that as you go, you find that you do your count like that. Then maths comes along and says, I want to put a distribution curve on that, and you get your classic normal distribution curve, bell-shaped curve. So when we talk about normal, even colloquially, we actually literally just mean most common. There is nothing that is called normal. It is most common now that people have to stay in their houses and are allowed out to make videos for their students to inspire them to learn stuff more with greater depth and understanding. But that didn't used to be the normal. The environment changed. Okay, so what is directional selection? So let's take this concept of, it was in the middle, you had this reasonably moist, open grassland, wasn't hugely windy, and then a new species arrived. So actually it was a biotic factor that changed the environment. A new species arrived, and it was a low-lying shrub, but a low-lying shrub is still taller than a small grass or a middle grass. Okay, so we get the introduction of introduce new species. So introduce something that means that it's not the best being in the middle anymore. So what happens? Well, these die out first. They don't breed. They get sheltered. They don't get enough light. They don't get enough, therefore, energy through photosynthesis to produce seeds. So they're done for. Well, already you can see the curve is moving slightly. These will be the next to go. Okay, but in actual fact, what you find is that's going up, that's going up. Probably even you have to extend the axes, because probably you even get a few new mutations that will be selected for, because actually the taller you are, the better. And over time, every breeding incident, this takes, depending on how quickly a species reproduces, it could take decades, it could take centuries. It depends how catastrophic the change in the environment is, really. That also dictates speed. So reproduction rate and the damaging nature or the strength of the environmental change, they dictate speed. Okay, so what we're doing now is our normal distribution curve is moving, because although these middle ones don't die, there are fewer. And so you can see we're going to have to start putting a new, I'll make that really fit with the textbook. You can see that we're going to a new normal. Now, what I've accidentally done here is showing that it could be that actually this whole species becomes less abundant, because actually my curve is never as high. And what's happening here is that selection is happening in a direction. It's moving towards taller plants. And that gives you that very, very tall one. And it's just an imaginary, made-up problem, environmental problem, this light one, but it's something that all plants would face. They cannot move into the light as such, so therefore they have to, they would be selected for in a non-mobile way. They could be taller. Tall ones survive, we move in a particular direction. So that's directional selection. Here we're actually going from A to B because I have one environmental change. So I'm not necessarily increasing the number of species. Of course, this could be in a fixed place. So A could carry on existing. So actually we might now have A plus B. So A exists where that shrub didn't manage to introduce itself. And so that you have A and you have B. So you've doubled the number of grass species. Okay, so now let's take our tall grass species, our brand new species. Okay, same graph. It's just now we're focusing on our new tall species, and we've reintroduced our normal distribution curve. Okay, it's taken many years to do this. However, it turns out that actually there is a... That's better. Oh dear, harsh. Okay, but now we find that we've got a huge, wide spread of alleles. Look, we go right from this tallest plant down to the smaller plant. Now we can say this taller plant has become a new species only when it cannot interbreed with the old smaller species. So therefore, again, it's a model to explain the graph, but in order to not be able to breed, many other different alleles would probably be selected for, and we have to ignore those to understand the model. But so we've got a new species, this tall grass no longer interbreeds with the smaller grass, so therefore we're going to say done, nailed it. But there'll come a time when that habitat potentially settles down, and it settles down to a competition between this shrub and this tall grass, and there will become a height that the shrub gets, the environment, that will be a set point, and there'll be then, if you like, the best height. We don't use too much energy to get too tall and become susceptible to any wind. So the very tallest alleles that have come about through mutation are selected against, but only the tallest, okay? So I'll pop our original normal distribution curve on there like that, okay, for this new very genetically diverse species. And you've still got their smallish ones, the smallest version of the tall grass. They're still less likely to reproduce, and so slowly they disappear as well. And so now you've got the second form of selection. You had this huge genetic diversity, but actually still the extremes weren't as good. And when we say as good, they didn't produce as many offspring. So therefore, the frequency in the population was very, very low. So although they were great and they give the plant more opportunity if the environment should change, of course, that's not what Darwinian evolution is. You can't, it's not preemptive. It works in that moment, in that reproductive cycle. So what we say is those ones in the middle have now become the most dominant alleles and the others are bred out. And what we've done is we've stabilised that species to a smaller distribution of alleles. So when you take off one end of the alleles and you push a species into a particular direction, that is directional selection. And then once a species is established and the environment does not change, that it requires environmental stability for this, you stabilise the selection around a smaller number of alleles. So this is stabilising selection. Okay, so that is it happening in the wild. And I was just walking, and just on the common, just to find the last little bit, just on this common, there's the other part of ecology, because I've talked about in this model where there's one perfect type of grass, but there isn't, because in actual fact, of course, I found the sturdy one, the thick with the big seed head here. I found the incredibly tall one with the very flowery, flowing seed head here. I'm sitting in the grass, so I've obviously lost all the others I found. Right, here's another one with a more delicate, that's 3 species already. I have to be careful, because if someone sees this and I accidentally pick up a sedge, not a grass, I'll be in trouble. So we'll leave it at those 3. There are also ones that aren't flowering. Grasses are incredibly hard to tell which is which until they've got their flower. I've got 3 species in one place, so how does that work? Well, they're competing with one another, and there's advantages, disadvantages. Okay, so it's not even June yet, and some of the grasses are flowering. Some come much later. If you like, that's a kind of physiological adaptation. When in the year do you flower? Because of course we just recently had a very, very cold week, and so some grasses that flowered too early, that's it, they've lost their chance this year to reproduce. And so it's a gamble. Everything's a gamble. I've actually just found out a 4th species. I think they're different, just given the difference in height, although the seed head looks very, very similar. And so what's happening here is, going to the ecology that you've done, or the biodiversity studies you've done, is every single one of those 4, or we'll call it 3 grasses, operates in a very, very narrow bit of the environment. It operates in its niche. And Darwinian evolution allows, with no competition, a single species per niche. So if there is enough light, if there is enough space, so that none of these grasses are sort of competing for that, they can all exist. They all exist in their very own little niche. Now, as soon as you get another species that operates in the same niche, you will get direct competition. And that's not necessarily a bad thing for a species survival, because you only then select the best of the best. So there you go. My next videos from here will just be going over that ecology and the value of it, the value of understanding how to study it, not just the value, pure esoteric value of knowing what you're looking at, but just the real, genuine value to humans. And I think it's very pertinent at this time, because I think one of those values has increased astronomically. Anyway, there you go. Directional selection and stabilising selection. The textbook looks at the absolute classic stabilising selection, which is at the moment human baby body mass. Too small and the baby struggles to survive. This is natural births without medical intervention. So too small, it's very unlikely the baby survives, so that selects against that. So you stabilise towards a particular weight. Too big and the baby could kill the mother at birth, so therefore that is selected against, because without medical intervention and no mother would mean no baby survives. So you get around a human body weight. But what's really interesting is, have we, by the introduction of medical intervention, restarted directional selection? Because if it's better for the survival and future reproductive success of a baby to be born bigger, well, now we have C-sections. You can have bigger babies, but the mother won't die. So has medicine, rather than in most cases got rid of natural selection in humans, has medicine reintroduced directional selection? Could babies be getting bigger? Anyway, I'll leave you with that. Have a lovely day, everyone.